Now, as the current starts flowing through the inductor, it does not actually have to move through it. Let's imagine another situation in which a battery goes off, or the current flow is stopped, or is taken off, or something like that. In such a case, the bulb will still not go off, it will still be burning. How does that happen? It's due to the inductor, guys. Remember, we had an inductor here. This inductor, which is acting as a short circuit, is actually storing the electrical energy or the current that is flowing through it in its magnetic field. Remember, I had told you that a magnetic field is developed around the conductor, which is being used as the which is technically the closed loop, or the coil in this case. So this is storing energy. When the battery is taken off, there is no more current supply. In such cases, the inductor starts providing current to the bulb. How does that happen? Let me show you. Imagine in this case, the battery is taken off. This is a filament again. People have to excuse my drawing. I'm really bad at drawing, guys. Okay, this is an inductor. Now, the battery is taken off and the bulb is here. This is still a resistor, and this is the inductor. And there is a magnetic field around the inductor, right? This magnetic field now, since the battery is taken off, there is no more current supply. And yeah, that's it. So this magnetic field was initially developed due to the presence of current, right? That's a property of current. It develops a magnetic field, around the conductor in which the current flows. Now, since there is no current supply, the magnetic field starts vanishing, guys. Guess what? Yeah, it starts vanishing. And since it starts vanishing, there is a change in the magnetic flux again. This is the game changer. There is a change in the magnetic flux, due to which there is the development of a voltage, or EMF, by Faraday's law. This EMF supplies energy to the bulb. And from where does it supply energy? The energy that was stored in the inductor, when current started flowing through the inductor, is stored in the magnetic field. When the magnetic field starts vanishing slowly, the energy that is stored in the magnetic field gets converted to electrical energy. That electrical energy is supplied to the bulb. That's it, guys. This is the thing. The EMF that is developed due to the change in magnetic flux initiates the supply of current to the bulb. So the bulb doesn't go off, even though the battery is taken off. So if we can get a short amount of, for a short amount of time, we can have a steady supply of current or energy to the bulb without it having to go off. This is it, guys. This is just how an inductor works. I think that answered our second question too. Now, how do inductors work? I think the last two questions are really easy. How do they look? An inductor is technically a coil, guys. It's a coil made out of metal. It looks somewhat like this. Even in real life, it looks somewhat like this. And the magnetic field is developed like this around the conductor. This magnetic field is the game changer in supplying energy. Now, you guys may have a doubt in your head. Okay, now Anush told me that there is energy stored in the magnetic field, and that energy gets converted to electric energy. But what is the magnitude of that energy? There is an expression for that. E is equal to half I square into L, which can also be written as half Li square. Which can be written as half Li square. What is L in this case? L is inductance. Whoa, we got a new term, man. We got a new term, inductance. What is inductance? Inductance, as a definition, is the tendency of an electric conductor, which in this case is this coil, which is being used as an inductor, is the tendency of an electric conductor to oppose the electric current flowing through it. What is this? Tendency of an electric conductor to oppose the electric current flowing through it. Guys, I just already told you at the start. Always, an inductor opposes the change in current through it. This is it. This is the property of an inductor. This is exactly inductance, yeah. Guys, I told you that this is a result that we have to assume at the start. But now here, look at this. The tendency of an electric conductor to oppose the electric current flowing through it. And why does it oppose the electric current flowing through it? It opposes due to the back EMF that is developed. Where is that? Due to the back EMF that is developed in the inductor. Okay, that answered our third question too. Our first question, what is inductor? I have answered here. How do inductors work? I have answered here. And now, how do they look? I have answered that question too. You guys have to excuse my drawing, but I've come quite close, guys. This is how an inductor looks almost. This is an expression for the energy that is stored in the magnetic field in the inductor, right? Let's keep this aside now. I'll bring it back to you. You guys may have another doubt now. Okay, now he told me that the current starts flowing through the inductor. Initially, the current will be very less, but as the magnetic field through the inductor reaches a certain maximum value, current starts flowing steadily. What I told was right. Let me explain it to you now. If we plot a graph of growth of current in the inductor versus time, the growth of current, the graph looks somewhat like this. The current starts increasing steadily, and it caps off at a certain value. This is actually analogous to the magnetic field too. The magnetic field starts increasing slightly, but again, as it reaches a maximum value, it caps off, right? There is an expression for this. Growth of current in an inductor is given by I naught, which is the maximum current that is possible, into 1 minus e to the power RT by L. What is R, guys? R is just the resistance or the bulb that we were talking about initially. Remember the bulb? Yeah, that's it. The bulb acts, as I already told you, acts as a resistance in the circuit. This R is the same R that we are using here. And this L is the inductance. And what is inductance? Tendency of an electric conductor to oppose the electric current flowing through it. This is inductance. Right. Now, this is growth of current. Let me write it here. Growth of current. Yeah, that's it. Now, this is when the battery is still there in the circuit. Where is the battery, guys? Okay, yeah, here's the battery. When the battery is connected, current is steadily starts flowing. This constitutes the growth part. When the battery is removed in the second case, in this case, battery is not there. Current starts decaying or current starts decreasing, or the inductor starts supplying the energy to the bulb. Right. Now, that process where the inductor starts providing energy to the bulb is called decay of current. Right. Here we are. Decay of current. It has a graph for that too. The graph is like this. It's a hyperbola, as you can guys see it. And the decay of current, the expression can be given by I of t is equal to I naught into e to the power RT by L. Again, I naught is a maximum value, e to the power, okay, wait, it's not minus, excuse. RT by L, I of t is equal to I naught into e to the power RT by L. This is it, guys. This is the whole concept. This is the growth of current. This is the decay of current. That's it. This is how an inductor works. And this is just more like a theoretical part. You know, if someone asks you, give me the expression for growth of current or give me the expression for decay of current, this should serve it. Let's recap. This is the expression for the energy stored in the magnetic field that is induced in the inductor. Right? Yeah, that's it. I think that should do it, guys, for this video, because I've covered almost everything here. What is an inductor? How do inductors work? How do they look? And yeah, one more question. Where do we use them?